let's go back to our minimal or minimum spanning tree. And Jacobs had a fair question about the practicality of this, right? So the main, again, still the main usage is in these type of network design, right? Could be cabling, could be electricity, could be again between cities, telecommunications. But what's more interesting is that actually there are harder problems, such as famous traveling salesman problem, any type of where you have to make a minimum pass. You want to travel between cities, you have heard of traveling salesman problem, right? Some of you have, right? Maybe a little bit. Yeah. It's considered like basically one of the hardest problems, but completely it's been proven it's not feasible to solve it in polynomial time in general case. But we can use MST as part of making estimations, basically as solving an easier problem, basically. So MST is often used as sort of like giving you like, okay, here's a solution to some harder problems. It will work, right? Another example is something called Steiner tree. This is something I was not actually personally used before, right? This problem here. It looks very similar to, let me make smaller, right? This one here, right? So this looks like something we discussed, like a minimum spanning tree, right? Because minimum spanning tree is, you could say, Steiner problem is like is a harder or more specific case, meaning you have different type of edges. You have normal terminal vertices, and you have sort of like some other vertices, right? So you're again trying to minimize this cost again, right? But you have these in-between vertices, right? Which is don't have to have the minimum pass there. So it's kind of harder problem actually, it turns out. So, but we can use MST to solve this problem basically, right? So there are these two Steiner points. So yeah, so this is again another application of MST. You have more difficult problems because in real life, problems will be usually more difficult than MST problem, right? But we can use it to make an estimation. So that's another application. But what's interesting was also MST is also used for image processing as well. When you're comparing some pixels, things like that, actually for some image algorithms use MST. That's another application. And also my field of expertise actually, which is topic modeling and actually working with textual documents. We use it actually too. Underneath, some algorithms use MST underneath actually for determining how similar documents are, which is kind of interesting. So let me add these usages, possible usages to this materials. Now I need, of course, find the actual materials. Where is my? Oh, there we go. I think this one here. Yeah. So possible usages before we move to Kruskal's algorithm. Right. So problem statement. Right. Let's see. Right. Let me see here. Right. So usage. Maybe we have problem statement. Do we have anything else? Minimal, or minimum. Let me see if we can find some usages here. Alright. Maybe here. Let's do this algorithms. Algorithms. For solving MST and now applications, right? Or why should we care? Again, applications of MST, right? So I'll do this network design, general network related problems, right? Network design, meaning, so, you know, electricity grid, electricity. Let me add, I'm lazy. Let me add this, turn on. Yeah. Network design, electricity grid design, of course, is, yeah, original, right? This is the original. Yeah, Boruvka is the one of them, right? Yeah. The second, of course, like network cabling in a data center. Yeah, water supply, right? Again, notice again, so this does not account for redundancy, of course, right? You just have connection. So if you have a breakdown, like there's a wind, there's a storm, right? You'll need some sort of a backup maybe as well, right? You have to think, is this MST is just enough, of course, in real life too. Again, things, considerations to think about in real life. What happens if a cable pipe, right? So that might be real life in consideration. So now clustering. Yeah. So that turns out for clustering design, actually, this is like something I was not really thinking about it. It's actually MSTs underneath actually there, right? So there's my clustering, image processing. Yeah. So this is kind of interesting. Image processing, right? Text TF document clustering, right? This is what I use actually almost quite often, right? So MST can be used to represent the relationship between documents, but I really was not thinking about this, right? If you think again, oftentimes you want to have to look at the problem from a different side of the side, basically here, right? You have documents, right? Very actual problem today, right? We have different things you have to compare, right? How do you model this? How do you say, okay, are these things different, right? So let's see, you have some sort of weighting. You have some weights. Are these, is there plagiarism? Maybe there's, how much copy paste in this document? You have some weight. Let's see, you have some weight, and then you can sort of say, okay, this document A is more similar to B is similar to C. You have weights, obviously, right? So you can use MST to sort of find the shortest, well, not shortest path, I would not say shortest path, you can find similar documents, right? So the one thing, of course, the question is, if you have this long path, right, from A to say G, right, does this mean A, G is actually, are they similar, right? Well, they're not going to be completely similar, right, because A and B, of course, is going to be the most similar, right? So, I'm not really sure how actually, what's justification for using this, right? Because you would think you want sort of like make some other metrics, right? Use some other metrics, but I guess MST can be used to identify the clusters, right? That's why I'm saying clustering, right? So you can see, okay, you take some subsections, and those, assuming you have some sort of cutoff points, you have some specific weights, domain specific, like okay, 0.6 similarity, that's good. 0.3, okay, those are not similar at all, right? You can use that as sort of cutoffs, for example, right? That would be something you can use, right? And also, of course, social network analysis, of course, again, social network analysis, I think, yeah, right? Community. So, which, if you think about it, it's very similar, right? So, they all three problems seems like completely different problems. They actually turn out, very, very similar. Again, so machine learning, actually, again, big topic, right, for next semester, right? Clustering, right, is one of the subjects of machine learning. So fields, right, study basically, right? So MST is part of this tool set of building these solutions, basically, right? So again, MST, in this case, the weight is going to be some sort of how good the buddies they are, how good the friends they are, right? Again, of course, the challenge is how do we come up with these metrics again, right? So one thing is our algorithms. Second thing is actually the data that comes in, right? You have, again, old saying, garbage in, garbage out, right? You have some really bad, you say these are friends, they actually hate each other, right? It's going to break the whole thing, right? So that's the thing. Or maybe they're frenemies, I don't know, right? So, okay. But yeah, so it seems like, so again, so takeaway from all above, so considerations, so above problems are rather similar. Yeah. So that's the difference. Yeah. So of course, clusters, you might have you will have a graph, generic graph. Okay. And last thing, of course, here I mentioned this is approximation algorithms. So classical example is traveling salesman, of course, right? TSP, right? So basically, I think if I remember correctly, it will guarantee, I think, twice the cost, which seems like kind of long, but it's still a good estimate, right? I think MST will guarantee, yeah, 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 yeah. So starting point, right? Yeah, so that's the thing. The other ones, yeah. So again, facility location problem or warehouse, you have again, this is again real life problem, right? Amazon faced this problem. So if you're working for Amazon, logistics, obviously you will encounter MST, right? So you need to, you're building this warehouse, again you work for Rimi or for Maxima or for Lidl or whatever, right? You want to minimize where you're going to place the warehouse, right? So because you need to, you don't put them, I don't know, in I'm sorry, Aluksne or somewhere, right, where it's not very useful, right? Unless there's some other factors, right? So, like you see when you drive around, of course, city in Riga, right, you see these big logistics centers, right, where they're located, right? There's some certain considerations why they are, right? Of course, near airports, right, near the city borders, right, where it's easy to unload, of course. There's some other considerations, but also, I am, 99% certain, right, that there was consideration how you can travel from those logistics warehouses to the other locations in the city, right? Others, of course, in this case, being stores, right? So you have the warehouses, and the nodes are the stores, right? Here, right? So, again, so that's a very, so think of, so it could be a supermarket chain trying to identify, yeah, new logistics service stores, for example. Right, okay. On, I don't know, other applications, is there anything else we can do? I'm trying to see if there was anything else. Was there anything else? Oh, yeah, a median. Oh, yeah, there's a median problem, right? Yeah, but this is, so this is also called, this could be called K-median problem, yeah. K-center, right, or K-center or K-median problem, or K-median, right, problem. What was it? Right. And finally, the Steiner tree. Steiner tree problem, right? Docs more on Steiner tree, right? Okay, so we added some little background why we should care about this, right? So it again, in real life, of course, again, the algorithm sits underneath, so you don't even think about it. But okay, let's now let's look at Kruskal's algorithm, which in some ways is very easy, right? But it has one tricky step actually. So MST applications commit. So now you see this. So we sort the edges, right? On have empty graph, nothing, just nodes, right? And again, you pick. So this part here is easy, right? So you have sorted edges. You guys know how to sort, right? But this is a tricky part, basically, right? If adding the edge to the subgraph does not create a cycle, right? Loop. And how in the world do you determine that, actually, right? It's kind of tricky, right? So if adding the edge, if you create a loop, you ignore this and you put it in the garbage, right? You don't need this edge anymore, right? It's not going to be useful, right? So you stop, you go through all. So when do you stop? You stop there to basically when you have n minus edges, right? Which is guarantees, or all vertices are in a subgraph. Same thing, basically, right? So and then you return the subgraph. So it's relatively simple. I think again, sorting easy, right? But this part here, right? This part here requires a really kind of funky data structure. The union find data structure, which is something you can optimize. So sometimes another takeaway of this is that sometimes if you need to do something many times, you can find maybe less used data structure for a specific task, of course, which is not going to be good for a general case. Not going to be an array or a general list, but basically very specific one, and it might actually be more efficient than using general structure, right? So this is going to be tricky, right? It's called disjoint set data structure, right? Because we want to do it as quickly as possible, we keep doing it, right? Of course, if you do it with some other data structure, what's going to happen? You're just going to have a really bad complexity, right? It's just like, again, checking for membership in a list on an array, right? It's slow, right? There's something in an array, right? But if you have a set, which is using hashes underneath, of course, right? We'll talk about hash data structures in a couple of lectures, actually. So, all right. So disjoint set data structure, right? So you basically have two operations: find and union, right? Basically, you need to find, right? And union is merge, basically, right? So in the beginning, each vertex is its own subset, right? No, they're all floating around all alone, right? And they eventually keep merging, right? So, right, as we add edges, we perform find, right? And if the subsets are different, meaning they're not in the same, so basically saying, okay, these are not in a different set, right? We can safely add it to the edge, right? So, and then we can perform this union operation, basically, right? So, all right, if the subsets same, if subsets are same, you will basically just put it in the garbage at the edge, right? So how do we take the cycle? We check whether two endpoints of an edge belong to the same subset, right? Endpoints, right? So we check the, A and B, are they already in the subset? If they are, the cycle, we just say, okay, go away. We have no need of it, right? So, all right, so this is the implementation, and let's see if this is actually decent, right? So it keeps track of connected components of subgraph, right? So without this, it's going to be really, really bad the solution. And with this, it becomes actually quite a decent solution. So class disjoint set. Let's take a look. Actually, we have parent, right, and we have ranks, basically, right? So the thing is, there's a list actually here. I wonder if there's, again, I don't know if it's actually completely efficient, actually, right? So, is it if self parent, right? Self find, because this one is actually a list structure. So this here, I think is, I'm very suspicious of this particular implementation, actually, right? We have find and union, right? So find, and if self rank pi pg, right? We find them, right? So if they are the same, right? So if rank, so it's hierarchical structure, actually, right? And then, of course, if this works, right? If this works, initialization, right? Self, right? I would like to rewrite this actually, but I don't know. Right, so Kruskal, the actual algorithm is ridiculously simple, right? You have you add graphs, right? You add edges, basically, right? Then we sort them. That's easy, right? Because we have the weight, right? We have the weights, right? We sort them, right? And notice something here, right? I'm going to be using a matrix, right? So who can tell me what's happening here, this part here, right? This second loop. This kind of the range. What am I doing here? Why is this? Why am I not going through all of them? Right, a matrix, right? Remember, this is matrix. Maybe I'll make this a little bigger. So it's two nested loops, right? So basically, this initialization, right? We have a graph coming in, right? So incoming graph is, I'll write comment. Control Z. Yeah, on incoming adjacency matrix, right? So why am I doing this weird thing here? What's happening here?
Well, so you don't check it against itself.
Yeah, basic idea is adjacency matrix, right? You have a basically it's a undirected, right?
Yes.
So we want only the top triangle, basically, right? Again, I'll draw this right here, right? So again, let's do another paint. Another paint job. Let's do another paint job. Yeah. So this part here, like you have a have something like, 3, 3, right? I'll do this, maybe 0, 0, right? 5, 5, right? Yeah. And like 8, 8, right? And let's say 2, 2, right? And maybe 0, 0. Okay. But then the point is that when you're building this this data, right? You only need only one half, right? Basically, So in this case, with these two loops, you only add this information because this is symmetrical and redundant in this case, right? So yeah, that's the whole point. So that is the point of these two nested loops, right? So again, now we added and we sort, right? Again, since we added weight as first element, we can sort edges, but without any specifying anything else, right? Right. So because it's going to be sorted, right? And of course, then these are tuples, right? We're adding tuples. So we are adding weight as first element and source destination, of course, same basically, and then vertices, right? So okay, now that looks pretty good, actually, right? Again, of course, I would like to rewrite this to have more generic, better names, and now it has to be all numeric. And then we initialize this disjoint set, right? And we are going to find them, right? They are basically going to create a union, basically here, right? We check, and we still append, right? We append this edge, right? Now the question is if length, this is when we stop, right? Here we print, right? Found MST, yay.
Question: the Kruskal's algorithm overall is less efficient.
No, it has specific use. So the thing is, let's think about this now. The complexities, right? The complexities. Now let's. It turns out that I like prims better, but actually there's Kruskal's algorithm, right? The complexity is, well, I don't know, geeks or geeks. This is good. So they're okay, but sometimes, but they don't know. So the complexity is number of edges times log v, right? So number of edges times log v, right? So this is going to be what? Good for, well, it seems to be good for, again, sparse. But again, if you have sparse, how about prims? Again, let me now compare with prims. Maybe prims algorithm. Again. Right. Right. Oh, we got also prims can be made for maze generation. Actually, turns out. Okay. But where's complexity for prims?
It was a little bit higher.
Yeah. So let me double check. Yeah. Okay. Right. So. Yeah, again, depends. Priority queue, of course, would be something we can use, binary heap or Fibonacci heap.
So it could be basically the same if you use binary heap.
Yes. So yeah, exactly same actually, right? So I kind of, well, I don't like this. This seems like the data structure. To me seems easier because heaps. I know heap much better than these disjoint data sets, right? So you have to be really careful because. About this data structure you use, because here, right, it looks okay, but let's see, I'm not 100% sure this is if you're looking fine, right, this part here is linear, right, so that's kind of really makes me a little bit afraid of this, if this is actually a good implementation, right, of this disjoint data set. So that's crucial. Otherwise, it's easier if you assume the black box of this joint data set is very good, actually, right? So then it's good, right? But otherwise, no. So we add this, right? So basically we do this. We check. So we check. We add edge if it does not if the vertices are not the same set, basically, right? Yeah. Let's see. Continue. We could do. Let's do this. Actually, I'm going to rewrite this. Actually, right? How I'm going to write it? I'm going to write it with continue, right? So, if find equal, right? I'll rewrite this. Right? Continue, right? And then I like flat code actually, right? So this we gain, right? So we continue if, yeah, we ignore, so we ignore maybe if it creates a cycle, right? So this is another little trick for you, for your coders, right? Otherwise you can end up, you don't want to end up with like 6 or 8 or 10 levels deep if statements, right? So this makes it a little bit flatter. Again, this is just a little cosmetic thing, but I think it makes it a little bit easier, right? So let's see if this still works, right? Now, right, this extra case. We keep going, right? We have early exit, so early exit condition. So early exit. Yeah, if we have right. So yeah, simple algorithm, right? Assume these two. So easy algorithm. So crucial. So for Kruskal, it's crucial. Kruskal, yeah, it is crucial. It is crucial that we have a good DST implementation. Else it all breaks down. Okay, now let's see if this works actually, right? Okay, so this is what? This is a really stupid one, right? But let's do something. Let's add something here, right? Let's add something like 3, 3, right? So this means from A, B, C, D, right? So again, A equals is 1, right? And so, right? So 3, C and D is connected with cheaper, right? So you have something more interesting, right? Print. No. Print the graph. Yeah, okay. Now let's do it. So you should find what? Not this one, right? You should find what? 0, 1, 5. Yeah. But it's actually no. It should be what should we print first? You should print this one first. You should print what? 2, 3, and 3. Or I'll make it maybe. Let's make it like maybe 2, 3, 4. I'll make it 4. Right. Let's make it 4. So it's more obvious. Right. So you should print out 2, 3, 4. Then only 0, 3, 0, 1, 5, and 0, 3, 6. Right. I think that's going to be. Let's take a look again. Yeah. Yeah, 2, 3, 4, like I said, 0, 1, 5, and 0, 3, 6. Right, makes sense?
Yes.
Yeah. So yeah, it's a simple. I think it's a simple algorithm if you have the disjoint data set. So this would be extra challenge, or maybe more for data structures class to think how this data structure implementation is actually optimal. All right. And now we can go on to the other one, Boruvka's, which is the last one, which the book really likes. Jeff really likes the Boruvka's algorithm, right? And his approach is like this. Let's show you what he says. He says this one, right? Basically, merge, right? It's basically you start at every node in parallel. So it has advantage. If you have a multiple CPU cores, you can parallelize this algorithm. That's a good advantage of it actually, right? So for modern day, this is a good algorithm. So add all safe edges, meaning you can add. So this is the approach. Maybe I'll show it to you a little bigger, right? So how it works. It's even easier, right? Recursively, right? So you find the cheapest. Initially everybody is disjoint, no connections, right? So you basically find connections, right? Immediately, right? So each node gets its cheapest connection to some node, right? Right. So the question is, can you create a loop with the first step? Safe. Yeah. So if it does not create a loop, you do it, right? So notice how each one, sometimes in 2 cases, this is for both nodes, right? It's the safest one. Sometimes it's only for one node, right? So after the first run in parallel, right, you end up with this, right? And then you find the safe edge, and you find basically, right? So only 2 loops, 2 iterations, right? Looks very efficient, right? So, but again, right? Again, easy if you, simple, but I think harder to implement this one correctly, personally, right? again, I think this is the most efficient one, assuming you have multiple CPUs, right, or multiple processing units of some sort, right? But not easy also to go wrong, right? But again, the same approach, same principle applies. You don't add something if it creates a loop. So we can use from Kruskal's algorithm, we can use same approach, same structure, disjointed structure. We can use that one. Let's see if I have it done actually. Let me add this Kruskal. Fixed up. So let me add this to do for this DSU. Check. Efficiently. It's efficient. It's correct, but efficiently. No. Boruvka. So where's my Boruvka? Or I can't. I'm not. I don't know. Anyway, anybody speaks Czechoslovakian? No, Czech. No. Not the. Yeah. No. Right. Yeah. Otakar Boruvka. Right. So initialize subgraph with each vertex, right? And basically for each subgraph, find the cheapest connection to something else outside, basically, right? So, and you merge, basically, add this minimum edge and wedge, right? So, maybe possible have some duplicates, possibly, right? Because if you have two connections, right, basically, right? So, stop when all vertices are included in a single subgraph, right? So, just priority queue, I don't know. It's E log V, right? Again, same thing actually. But, right, so for sparse ones, it's actually, I think, not as good. So is this going to work with heap Q? I thought we had to use the disjoint. Let's see, this actually works. I'm kind of curious. So Boruvka MST, length, subgraphs, right? I think you need disjoint here. It's not going to be as good. But priority Q works, but heap Q again. So we have our graph, right? We have our subgraphs, right? Basically, originally, right? Yeah. So originally we have, n subgraphs, right? Because they're all disjoint. You'll have to start joining. Yeah. So this part is going to be, yeah. So this part here is, we need to start adding them together, basically, right? Merge. And the question is now, do we have anywhere, remove duplicate edges, right? So while length, right? So this is a non-recursive solution. Right? So enumerate subgraphs. So this looks like 1, 2, 3. Yeah, this is not the most efficient solution, I believe. Right? You have 3 loops, right? And this is also a loop. So 4 loops, right? And that's not probably looks like cubic at least, right? So this on J subgraph, right? Yeah. So this is not efficient solution. All right, but let's see. Let's see if this actually works. Alright, don't fix me. I tried to do this, but actually this is pretty bad, I think. Do we still have a graph? Do we still have a graph? Print current graph. Yeah, we still have a, oh no, that's G. Okay, yeah. Alright, so let's try it. I don't know what's going to happen. It's going to, I think, break. I think I tried it. Oh yeah, so default dictionary. Yeah, this is going to be a different solution. I think this one breaks. This one doesn't work. Print. Yeah, I think this one is broken. Yeah, index errors. There's index. So this part here, right? List index. There's an index error here, basically, right? So this one is a bad implementation, I think. And also, it's very suspicious because it's these loops. I think I should just delete this one here, right? With priority queue, because it's not really supposed to use. So default dictionary, right? This looks better, right? We have at least a graph, right? Vertices, default dictionary. We add edge, find, right? We have union, right? This looks more promising, right? I like this better. Yeah. We of course add this. Yeah. This is from, I think, from Geeks for Geeks, looks like. Yeah, this looks like from Geeks to Geeks. Yeah. Yeah, this is from this one. But of course, again, you sometimes need to go through these and actually check if it's actually correct. But let's see. I think I gave up on this one. Alright, weight is MST, but we would like to, of course, find. Yeah, so in this particular case, 0, 1, 10, 5, 4, right. Look, it looks okay to me, right? Looks like to me okay. Documentation, docs, site. Yeah, I believe this one here. Let's see. This, I think this is one. Yeah. Yep. Yeah, this is Boruvka, right? So you can see it here again. So what's happening? You start with nothing, right? All disjoint, and then you keep adding. You add immediately, right? Sometimes you have bigger chains, right? Sometimes you have small chains. So here it's almost, you have only 3 islands, right? This one, this one, this one, and then basically for each, right? It's possible that you find, 8 and 8 here, right? It's possible the algorithm you get multiple additions, right? But your the check whether it's actually needed, you will basically how should I say? You will not allow adding the second 8 basically here. Of course, you add 7 here, right? Yeah, 7 and 8 somewhere, right? So you add 7 and 8, right? Where is it going to be? Or 4. Sorry, I missed 4. Yeah, sorry, I missed 4. And then, but then 8 is actually more important. Actually, it's interesting. So 7 is not needed here, right? Because we have 4, right? Well, then 1 8. This 1 8 also would work, by the way, right? This or this doesn't matter, right? But this 4, of course, is more important than 7 here. Okay, right? Yeah. So this is what I think we use. Naval. No, this different guy. This guy here. You see, somebody took somebody else. Somebody else's credits. I don't want to. I want to give proper credit to this guy here. Right. It's not what I wrote myself. So we are like 1 minute, so I wouldn't have time to make improvements. The one big improvement I would like to see in this implementation-wise to have some sort of more generic, edges and weights, not to have numeric nodes basically, right? So you can use arbitrary nodes basically. So where are we? Yeah. Right. All right. So that this works as well. But this find, self-find, it also, I don't think it's also optimal, I don't think, right? Union of 2 sets, find is what? So, parent, so if parent equals I, then self-find. So, this is recursive, right? Recursive call, right? And what are we using this? What kind of structure? We have vertices, right? And default dictionary. But this doesn't look like a dictionary to me. This looks like multiple list to me. Right here. And this is graph. Yeah. So, okay. Alright, okay. Oh, there's one more on this guy here, 93 actually. Somebody only 30 years ago, right? Linear time randomized algorithm, right? So this is actually, this is again extra credit basically. There is ways to improve this because this again, it is actually is an important problem, right? Basically, you do some randomness. So random approach being you sort of like random. You take random edges, right? Until you have only two vertices left, basically, right? You keep merging, basically, right? Replace edge connecting 2 endpoints with edges that connect the merged vertex, right? So, obviously, you have to handle the loops, right? So, initialize the graph, same vertices on edges as input graph. While there are more than 2 vertices, randomly choose an edge, right? Right? And you merge, basically. Interesting, right? This is very interesting. So, probability, this means is the more you run it, right, probabilistically you find the correct MST, right? Yeah. So basically, for sparse graphs, not so good, but good for actually very dense graphs, right? Because it it's V, and here is V, right? So V squared, right? So if you have E, right? If E is, remember E is in general in the worst case scenario E is V squared basically, right? So if you have a dense graph, right? This might be a good approach. Really wild actually, right? Really wild algorithm, right? So I couldn't get it to work actually, right? So here, yeah. So clustering, we have talked about this already, guys. So, right. So here's some extra resource if you're interested in this. But again, I think again in real life, of course, you check. You need to see whether your solution, like a possible solution, whether you have a lot of this dense graph, where you have lots of edges, right, close to the maximum, right. Then you probably use Boruvkas. Right? Again, you have a parallel approach, right? Even added little this Boruvka, right? On small graph, you can use prims, right? And of course, you can use whatever network next, whatever library supplies, right? That's another approach. Okay. Oh, they include this, okay? And if it's not slow, use that, right? So let me double check before we take a break. You guys comment? No. Okay. So, or anybody else has a comment on this topic? Probably on Thursday we'll practice on this. Let me see. Network X, for example, network X minimum spanning tree. Let's see what they use. You can also read how they implement it, right? So it's of course included, right? No, you have three choices. You have all three. You can use Kruskal, you can use Prim or Boruvka, right? Yeah, choose whichever, right? Default is Kruskal actually, right? Default is Kruskal, right? So that's kind of cool, right? They did all three, right? Yeah. So the thing is, the Boruvkas needs weight, right? Otherwise, again, remember, it's really if you have default weight 1, you can just use DFS. I mean, it will work, right? Or BFS actually, right? You don't really need this, but yeah. So yeah, use this. So let me do this. So let me add this here. So use it. Practical. Let me add here one more. Where's here? No. Here. Okay. Network. Library. Yeah. MST provides parameter for all three. Yeah. Yeah. Okay. All right. So let's take a break. We'll continue at 11.